Hi guys, welcome to Tutes Online. Today we'll be looking at triple integrals. Triple integrals, as the name suggests, is integrating a function 3 times, and this can be useful for calculating the volume of a shape. There are 3 different coordinate systems which you can use for triple integration. There is Cartesian, cylindrical, and spherical coordinates. Cartesian, cylindrical, spherical. Today we'll be looking at the Cartesian coordinates. We'll start with a very basic shape. Is our Cartesian coordinate system, x, y, and z. Give it a base, some height, and attempt to... So here we have a basic box, where say that's 1 high, that's 2, that's 3. And we want to find the volume of this box. One way to do this, which is what integration is you can make a tiny little cube, have a dx, dz, and a dy. And you can imagine this little cube as a grain of sugar, and you fill up this box with these grains. And the volume, dV, of this little sugar grain would be dx times dy times dz. So to integrate this box, we would say the integral of dx, which is the sum of all dx values, and also the integration of dy, and also the integration of dz, would give us the total volume. For triple integrals, order is important. Our first one is the x, which is this, and that's between 0, which is over here, and 3, here. Then we have y, between 0 and 2. And lastly, we have z, which is between 0 and 1. So we'll clear up some room. And now we'll solve this. We'll start with x, which is just this one. And we can imagine that there is a 1 here. The integral of 1 from 0 to 3 is just x. 0 to 3, which is 3 minus 0, which is 3. So rewriting this, putting our other integrals back in, we have our 0 to 2, and 0 to 1, and our dx is already done, so we've got dy, dz. Next, we'll do our y. So we've got our 0 to 1 already, and we just have 3y. From 2 to 0, dz equals 0 to 1 of 6 dz. And this is just simply 6. And if that was in meters, then we'd have meters cubed. For a more challenging example, sometimes the shape is bound between certain functions. For example, the volume of a solid bound between x squared plus y squared equals 9, which is a circle, z equals 1, and x plus z equals 5. It's best to draw these to get an idea for what the shape looks like. So you know the first one will look something like a circle between 3 and 3. The second one will look something like a straight line along Z. That's Z. These ones are X and Y. And the third one is a straight line. Well, that's 5. And that's 5. Well, that's Z. And that's the X. And using this, we need to find out what our limits are for our X, Y, and Z. First of all, we can see that Z is bound between 1, which is here, and this function. So rearranging for Z, we'd get 1, and Z equals 5 minus X. For Y, it is bound by this circle. Rearranging for Y, you get that being between negative the square root of 9 minus X squared and positive square root of 9 minus X squared. And for X, it's bound between negative 3 and 3. So putting this in our equation, we can say that the volume is equal to the integration from negative 3 to 3, which is our X, between negative the square root of 9 minus X squared and the square root of 9 minus X squared. And for Z, it's simply between 1 and 5 minus X. And we have our dz, dy, dx. To start solving this, we'll work on the z. So that's between negative 3 and 3, between etc. and etc. to save time. And this is, we have just a 1 here, so that's z. Between 5 minus x and 1, which we can write as simply 4 minus x dy dx. Scrolling down a bit, we'll now solve our dy. So between negative 3 and 3, so we'd be integrating this 4 minus x, which will simply be 4 minus x y, between square root of 9 minus x squared and negative 9 minus x squared dx. The x can be treated just as a constant, so this is really this one plus this one because it's a minus minus, so you'd end up with 2 4 minus x square root of 9 minus x squared dx, and that would be equal to make it look a bit neater, 8 minus x square root of 9 minus x squared. And we can treat this as two different functions now. So we've got the 8 and the x. And in integration, you could separate this. So we'll separate this by taking the 8 outside, taking the integral between negative 3 and 3. So this will be the square root of 9 minus x squared minus integral from negative 3 to 3 with the square root of 9 minus x squared. Put our dx's. This part gets a bit difficult because you have to use integration by substitution. A little mathematical trick is that if this is an even function, we only need to integrate half the function. To be even, our function 9 minus x squared would need to be the same if x were negative. That would be negative x squared, which is equal to square root of 9 minus x squared still. So it is an even function. So that means that we're able to integrate between 0 and 3, because we've just proven that one side of x is the same as the other. But we'll also have to do 2 times by 8, because we have 2 equal sides. Now if we look at this is a familiar thing from trigonometry. So for a triangle, that's theta, this would be 3, that would be x, and this would be our root 9 minus x squared. So we know that cos theta is equal to square root of 9 minus x squared over 3, so square root of 9 minus x squared equals 3 cos theta. Our x on 3 is sine theta, so x is equal to 3 sine theta, and therefore dx would be equal to 3 cos theta d theta. Rewriting our integral, we would have integral 2 minus 8 from 0 to 3. So this would be our 3 cos theta times by our 3 cos theta d theta. Now there's a relationship that says that 2 cos squared theta minus 1 equals cos 2 theta. Now rearranging our function, we could say that our 9 minus 8, so it's getting rid of these 3's and putting the 2 in there, from 0 to 3, and we have our 2 cos theta squared d theta. This would give us 72, integration from 0 to 3 of cos 2 theta plus 1 d theta. Move the page down. So now we can integrate this. So we know we can do it in 2 separate parts because we got the cos 2 theta and the 1. So the first one, 72 times by integration of cos 2 theta, which would be sine 2 theta on 2 plus theta between 3 and 0, or 0 and 3. So we previously said that sine theta is equal to x on 3. Therefore we can say that sine inverse of x on 3 equals theta. Get some more space, but we know these are for the x and not the theta, so you can't just sub them in. So we'll have 72. This can be rewritten as 2 sine theta cos theta plus our theta value, which is here, and this is equal to sine inverse x on 3, 0, more space. We can rewrite this as 72, and this has an equivalent 2 times by sine theta, which we know is our x on 3, and cos theta, which we know was our 9 minus x squared over 3, plus our inverse sine, x over 3. So we can rewrite this as 72 to x square root of 9 minus x squared over 9 plus inverse sine of x on 3. So now we can finally substitute. So this would be 72 outside of 2 times by 3 times by 9 minus 9 over 9, so that's a 0, plus inverse sine of 3 over 3, which is 1. Now we sub in 0 here, we'll get a 0, 0 here, we get sine of inverse sine of 0, which is 0. We get a bit more space. So what we have is 72 times by inverse sine of -1. Sine wave goes something like this. Its peak, which is 1, is at pi on 2. So therefore we have 36 pi. So if we look at what we were actually integrating, we solve this. If you solve this, you'll find that it's 0. Therefore, our final answer is 36 pi.